So, a little bit more information about this railroad spike Wootz that I've been working on. So, first thing that kind of came up as an issue in this is the odd shape of the railroad spikes. They were long enough that they came up close to the rim of the crucible. As soon as I saw that, I really should have paused, done something that I did later, which is just heat them up, fold them in half. And that actually has a second good effect. These were all super rusty. I didn't clean them off. This, the bending process and the heat, especially, that's involved in that converts a lot of the oxide from red oxide to a black oxide. And that black oxide, a little easier to deal with. Plus, a lot of it just flakes right off. So, like I said, that something I should have dealt with right at the beginning. I charged ahead and it bit me in the butt. So they, before I got to this nice solid ingot, and I've got some, some stills of that, which I think will get interspersed in here. Before I got to that solid ingot, I got a kind of crappy ingot. And the reason for that was A, all that oxide at the beginning, and B, the height of these. As soon as my glass melted and my small cast iron constituent melted, I think my actual liquid level was about halfway up the crucible, leaving the ends of all those just protruding up into the furnace atmosphere. And I do my best to keep a fairly neutral flame going in there, but in reality, there's no such thing as a neutral flame. If there is, if you've got exposed iron, it's going to oxidize at those kind of temperatures. That it's just reactive enough. It's going to happen, unless you have a super carburizing environment, as you do in, say, a bloomery stack, something like that. So I got a lot of oxidation. All that oxide actually, maybe not all of it, but a lot of it ends up in the melt. Has two things that it does. First, it combines with some of the carbon that I had put in. Therefore, I end up with a lower carbon content. Rather than that carbon becoming part of the steel, it becomes carbon monoxide, floats away. The other thing it does is that when the steel is liquid, it can dissolve quite a bit of gas. In this case, a lot of carbon monoxide. However, as it begins to solidify, it can no longer hold that, and you get a similar effect to, say, champagne, something like that, where suddenly all this carbon monoxide, carbon dioxide that has been in solution starts to bubble out during the solidification process. I just ended up with a very porous ingot. In some cases, you can actually have almost an eruptive state during that solidification. And that's the reason why in industry you kill the ingot, or kill the steel. That is by typically adding some aluminum. The aluminum is super reactive, sucks up all that oxygen, allowing your carbon monoxide to split, go back to being carbon and now aluminum oxide. Carbon goes back into solution in the steel, aluminum oxide becomes part of the slag. I've been trying to do less and less of that because this was not a historical method. They did not have aluminum to add. Aluminum did not really become a thing. It wasn't really discovered, I think, until the mid-1800s. Didn't become producible in any volume until, I feel like it was World War I, World War II, something like that. Somebody can, look that up on Google. Any case, so I had to melt this twice. In the second melt, I added a little bit more fresh material, so folded up spikes, along with some additional charcoal to bring my carbon content back up where I thought it needed to be. So, now that we've got the solid ingot, how do we forge it out? It's a little tricky to tell in watching the forging videos, so that's why I've got my little diagram here. Essentially, the way I forge out is so this top center area becomes one end of my forged bar. What I have found over time is that these dendrites that form, and dendrites are just a natural form of solidification. It's the crystals on your windshield. It's, basically anytime you see a liquid becoming a solid, in most cases, if it's not a pure substance, it will develop dendrites. And those dendrites, they start in a single point and spread in all directions. So there's not much organization to it. If you look at pictures of dendrites, it's just a weird, they kind of look like they're forming a grid. But when you look at it more closely, you realize that it's like a grid here and then a different grid over here. And now imagine that's three-dimensional. So you've got grid coming this way, that way. So within the ingot, there's really not much organization to that at all. So you can forge this any direction you want. The historical method would have been to take that ingot and squeeze it out this way, such that this top center area would become the spine of a single-edged blade. That's how most Wootz ingots were forged historically. And the reason they would do that is, if you imagine how you can hold something on an anvil, the easiest way to hold it is with this big flat down on the anvil, which doesn't naturally lead to this. What it leads to is first squashing down, making a little bit of a puck. Now that you've got a puck, so we've brought it down this way, and then you can stretch it out that way. And the reason that you're worried about where that top center is that's the very last part to solidify. And the last part to solidify ends up with the most impurities, the most porosity. So it is the crumbliest material. I've actually drawn in a little bit. I always get what I like to call the crunchy butt of the bar, and that just gets trimmed off, tossed into the next ingot. But what I've found over time is that because the dendrites start off oriented in every direction, it really doesn't matter which way you forge it, which direction you forge it out. You're going to get essentially the same pattern. I've tried all different ways. And actually, on this ingot, I do a little demonstration of that because after forging out to this stage, I trimmed off the crunchy butt, realized that I still had some odd cracking that extended further down. So I trimmed off a series of pieces until I got down to solid material. It's a real advantage of forging out this direction. When you forge out the traditional way, if you've got cracking material, you've stretched it over the full length of your bar. Now you got to grind down substantially if you want to get rid of that. Traditionally, they kind of actually just left it for the most part. As long as that was along the spine of a single-edged blade, it didn't actually have that much of a detrimental effect. Modern standards don't really allow for leaving giant cracking seams in your blade. So that's why I started forging out this other direction. I feel it yields a superior product, especially by modern standards. Now, since I had trimmed off these pieces, I decided to have a little fun with, what does the pattern look like if I forge out in different directions? Again, got some stills showing the orientation of those bars, those little chunks. Basically, those pieces, I took them and flattened them out as though, in that picture, it's as though they were sitting on the anvil. I tried to forge them all essentially the same way, the same heat cycles, etc. They are not hardened, so the pattern you see is a little different than what I typically get in my blades. And intriguingly, so two of them look almost identical. So, one of them I forged out this way, one of them I forged out that way. And those two look almost identical. At this point, with this much forging done, I've really established a grain to the material. So everything is definitely very linear in that bar. And at that point, it doesn't really matter which way you forge the bar. The last bar, I don't remember which number it is in the series, but there is another bar that I actually forged this way. It was a chunk I cut off, so I forged it so the end grain became the surface. And that one is quite different. And it's not surprising that it's quite different. You're really looking right at the end of steel that the grain had really been forged in the other direction previously. So the three are essentially, let's say, the face grain becomes the face of the bar, the edge grain becomes the face of the bar, or the end grain becomes the face of the bar. And those just kind of illustrate a little bit of what the pattern looks like in there at this stage in the forging. So I'll be moving on from here, but that's going to be another video. Got to break this up a little bit. The next stage, however, just for fun, I'm actually going to go back and forge a railroad spike so that we can make a usable railroad spike knife. Thanks for watching.